Dear students, today we are going to discuss about transfer function modeling in module 6. So first we can see what are mathematical models of control system. So in the previous presentation we discussed about the control system and the various components in a control system. So we know that a control system is a collection of physical objects or components connected together to serve an objective. So in a control system there will be inputs and outputs, and they are related by an equation called differential equation. So the mathematical model of a control system consists of a set of differential equation. The response or the output of the system can be studied by solving these differential equation. So in order to solve the differential equation, we should know what is the principle of superposition and homogeneity. So in the diagram, it shows the principle of superposition with the property of linearity. So in the diagram, we have two inputs, so R1 of t and R2 of t, and they are applied to two separate systems, and the output obtained are C1 of t and C2 of t. So when we apply the superposition theorem, or based on the linearity principle, superposition theorem combines the combination of the inputs R1 of t and R2 of t multiplied by the scalar values a1 and a2. So we'll be getting a1 R1 of t and a2 R2 of t. So the combined response will be the principle based on the principle of superposition theorem. So the output C3 of t is a1 C1 of t plus a2 C2 of t. Then the system G is said to be a linear system. The analysis of the differential equation require transfer function. So transfer function of a system is defined as ratio of Laplace transform of output to Laplace transform of input with zero initial condition. So in this presentation we are going to derive the mathematical models for mechanical translation systems and mechanical rotational systems. So first we can see about mechanical translation systems. The model of mechanical translation systems can be obtained using three basic elements: mass, spring and dashpot, because these three elements are the basic essential phenomena that occur in a mechanical system. So here the weight of the mechanical system is represented by the element mass, and it is assumed to be concentrated at the center of the body. The elastic deformation of the body can be represented as spring, and the friction existing in a rotating mechanical system can be represented as dashpot. So dashpot means a piston moving inside a cylinder filled with viscous fluid. So to derive the mechanical translation system model, it is based on the Newton's second law of motion. So when according to Newton's second law of motion, when a force is applied to a translational mechanical system, it is opposed by opposing forces due to mass, friction and elasticity of the system. So to derive the mechanical translation system model, the following symbols are required. So x represents displacement in meters and v represents velocity. So velocity can be written in terms of displacement as v equal to dx by dt. Velocity, the unit is represented in meter per second. Then acceleration a is equal to dv by dt. So acceleration is related to velocity by dv by dt and is related to displacement by d square x by dt square. The unit is meter per second square, and F is the applied force, and the opposing forces are due to the mass of the body, elasticity of the body and the friction of the body, where M is mass and K is stiffness of ring and B is viscous friction coefficient. Newton's second law helps to derive the force balance equation of these idealized elements. So here we are considering, in the diagram we are considering the ideal mass element. So F is the force applied, and consider an ideal mass element which has negligible friction and elasticity. So let a force F be applied on it. So the mass will offer an opposing force which is proportional to the acceleration of the body. So let F is equal to applied force, Fm is opposing force due to mass. So Fm, the opposing force, is proportional to acceleration. So acceleration d square x by dt square. So replacing the proportionality by a constant m, so Fm is equal to m into d square x by dt square. So by Newton's second law, F is equal to Fm is equal to m into d square x by dt square. Next we have consider an ideal friction element dashpot as shown in the figure. So this dashpot has negligible mass and elasticity. So assume a force applied on it. So the dashpot will offer an opposing force which is proportional to velocity of the body. So F is applied force, Fm opposing force due to friction. So F proportional to dx by dt, it is the velocity. So b into dx by dt, replacing the proportionality by a constant b. So according to Newton's second law, F is equal to Fb equal to b into dx by dt. Suppose the dashpot has displacement at both the ends, so here x1 and x2, so the difference we have to take. So Fb proportional to d by dt of x1 minus x2. So we can write according to Newton's second law, opposing force is equal to the force opposing force is equal to the force generated by the dashpot. So b into d by dt of x1 minus x2. Consider an ideal elastic spring element as shown in the figure, which has negligible mass and friction. So a force is applied on it. Naturally the spring will offer an opposing force which is proportional to the displacement of the body. So F applied force, Fk opposing force due to the elasticity. So Fk proportional to x, proportional to displacement. So replacing by constant k, so I will be getting F is equal to Fk equal to kx. If suppose the spring has displacement at both ends x1 and x2, so opposing force is proportional to the differential displacement. So F is equal to Fk equal to k into x1 minus x2. Mechanical rotational system. So now we are going to discuss about mechanical rotational system. The model of the rotational mechanical system can be obtained using three elements: moment of inertia J, represented as J, dashpot with rotational frictional coefficient represented as B, and torsional spring with stiffness K. So here the moment of inertia of the mass represents the weight of the rotational mechanical system, and it is concentrated at the center of gravity of the body. And torsional spring represents the elastic deformation of the body, and the dashpot represents the friction existing in a rotational mechanical system. So here are the symbols used in the mechanical rotational system. So theta represents angular displacement, and d theta by dt represents angular velocity, and d square theta by dt square is angular acceleration, and capital T is the applied torque, and J moment of inertia, and B rotational frictional coefficient, and K stiffness of the ring. So first we can see the ideal rotational mass using mass element. So here consider an ideal frictional mass element. So T represents the applied torque, and Tj represents the opposing torque due to the moment of inertia of the body. So Tj proportional to d square theta by dt square, replacing by the constant J. So according to Newton's second law, the opposing applied torque is equal to the opposing torque. So T equal to Tj equal to J d square theta by dt square. Then if suppose we have the ideal rotational dashpot, if you are considering, so ideal dashpot which has a negligible moment of inertia and elasticity, and we are applying a torque. So the dashpot will offer an opposing torque which is proportional to the angular velocity. So angular velocity is d theta by dt. So applied torque is equal to the opposing torque. So T equal to Tb, that is proportional to the angular velocity. So B into d theta by dt. Now you consider when the dashpot has angular displacement at both the ends, that is theta 1 and theta 2. Then the opposing torque is directly proportional to the differential angular velocity, that is d theta 1 by dt minus d theta 2 by dt. Now we have the ideal spring element. So ideal spring represented as K with one end fixed as reference. So here the applied torque is T. So T is the applied torque. So naturally the spring will generate an opposing torque Tk due to the elasticity of the spring. So Tk proportional to the displacement, that is theta. So replacing by the proportionality constant, it is k theta. If suppose when the spring has angular displacement at both the ends, like that's theta 1 and theta 2, and if the applied torque is capital T, the opposing torque is proportional to the differential angular displacement, that is theta 1 minus theta 2.